The Bohr model of the hydrogen atom. So here's Niels Bohr, just an amazing man. I'm sure you've heard of Einstein. Niels Bohr was a contemporary of Einstein. They were friends. Bohr was just an amazing man, an amazing scientist. 1885 to 1962, Danish physicist, Nobel laureate. Element 107 was named in his honor. In 1912, Niels Bohr devised a theory that explained both the emission spectra and how electrons move within an atom without losing energy. Remember that from our last notes, these were the two big puzzles. Why don't electrons collapse into the nucleus? Electrons are negatively charged, protons are positively charged in the nucleus, so why don't the electrons just crash into it? Also, what causes emission spectra? Why do we see emission lines when we look at elements who are energized and they give off light? Nobody knew. Niels Bohr came up with an amazing theory. Now I'm going to show you a video here of Niels Bohr, so kind of sit back and watch this. You can take notes. You don't need to, but some interesting things in this video.
One of the key figures in the quantum revolution is a young Dane with a tendency to mumble. He's the scientist on the right. His name is Niels Bohr. And from childhood, it's physics that consumes him. Once, while playing goalie in an important soccer game, he starts scribbling equations on a goalpost. Only the screams of an ardent fan snap him out of his reverie in time to stop an opposing player's potential goal. At school, he's an excellent student, though he seems to have a serious phobia about writing. As a graduate student, he dictates his entire doctoral dissertation to his mother, causing a family fight when his father insists that the budding PhD learn to write for himself. He never does. After his marriage, his wife gets the job. In 1912, shortly after receiving his doctorate, Bohr travels to England. He comes to Ernest Rutherford's laboratory just 1 year after Rutherford makes a startling discovery about atoms. Atoms had been seen as amorphous blobs of positive charge studded throughout with negative electrons. In fact, Rutherford says, they're more like little planetary systems. All the positive charge and virtually all the mass is concentrated in a tiny nucleus, around which the electrons orbit like planets around the sun. This is the courtyard at Cambridge University, where Rutherford began and ended his scientific career. Imagine an atom this size.
If we think of that being the size of an atom, then the size of the nucleus would only be 1 millimeter in diameter. That's a bit smaller than this little grain of sand that I've got in my hand here. In other words, what it means is atoms are essentially empty space.
Rutherford's conception of the atom is a breakthrough, but almost immediately he finds a paradox at the heart of it.
See, the problem was that if you've got a nucleus with a positive charge and electrons in orbit about it, then we know that the electron should very rapidly orbit into the nucleus. It should do it in a fraction of a second. That's a very secure prediction of classical physics. And that's catastrophic. What it's telling you is that atoms cannot exist. It means that you and I would not exist. The atoms would have no way of supporting themselves with the large volumes that they have.
When Niels Bohr arrives in Manchester, Rutherford is ready to abandon his model of the atom. But Bohr sees a way to save it.
He was so excited, he canceled his honeymoon. He had to delay his wedding, cancel the honeymoon, and his poor fiancée, instead of going on a luxurious honeymoon, had to take dictation as her husband dictated one of the greatest masterpieces in physics because he himself could not get himself to write down the paper.
What he proposed was that you would not allow the electrons to move in any orbit about the nucleus, as you could according to classical theory, but only to occupy certain very well-defined orbits about the nucleus. There would be an orbit here, an orbit here, an orbit here, but there would not exist orbits between these.
There's nothing in between. In between exists nothing. And that's very non-Newtonian. If you take the Earth and you could move the Earth a little bit closer to the Sun, no problem. It would have a different orbit, would be stable, would have a different time to go around the Sun, no problem. That you cannot do with an electron around a nucleus. You cannot just change the orbit by a little bit. You have to change it by, so to speak, a lot.
Bohr's idea that electrons can have only certain orbits draws inspiration from other new theories that suggest heat and light come in units that can't be divided, called quanta. But applying this quantum idea to matter is practically sacrilegious. In fact, most physicists disapprove of Bohr's theory. Whenever they meet, they scoff at the idea that an electron can be in some places but not others, that matter comes in some sizes but not others.
If it's not nonsense, at least it doesn't make sense.
This is just a cheap excuse for not knowing what's going on.
The assumptions are too bold, too fantastic. They can't be right.
In time, two camps emerge. A group around Bohr, which believes in his so-called quantum theory of matter, and those who cling to the classical view. No less than the true picture of nature is at stake.
All right, now let's look at Bohr's theory. Bohr's theory stated that electrons could exist only within allowed orbits that he called energy levels. So these circles around the nucleus, rather than referring to them as orbits, it kind of looks like they would be. Quite often you'll see the electrons going around an atom like a planet around the sun, but we're going to be referring to those as energy levels. So Bohr theorized that as long as the electrons were in these energy levels, that they could exist without losing energy. In between these energy levels, electrons could not exist. So it could not exist in between. In between, no. In between, no. But any one of these energy levels, it could exist. Now, why is that? Why would that be? So it was a very strange idea. Why couldn't the electrons just be anywhere? It's kind of like throwing a ball up. You could throw a ball any height that you want. But inside of an atom, you can't just have an electron go any distance from the nucleus. It needs to either be at this energy level or this energy level or this energy level. It can never be anywhere in between. A very, very strange idea. Allowed energy levels are most easily understood if an electron is thought of as a wave moving in an orbit around the nucleus. So here you have an electron wave. Such waves are referred to as de Broglie waves or matter waves, after Louis de Broglie, another Nobel laureate. All matter, I know this is a little bizarre and off topic here, but all matter travels in a wave. The more massive it is, the less the wave can be measured. But electrons are so very, very small that the wave can be measured. You may have heard of electron microscopes. It takes advantage of this property of electrons traveling in a wave. Just like a regular microscope can focus light rays, well, an electron microscope can focus electron waves. Within each energy level, an electron wave must superimpose or overlap on itself. So that can occur at the allowed energy levels. But if the electron tries to exist in between those energy levels, then the wave is not going to superimpose on itself. So when it does, it's referred to as being in phase. So everything is good. The electron can exist at that energy level. However, if it's at a distance where the waves do not overlap, then they cancel each other out. Anywhere in between the energy levels, the electron wave will interfere with itself and cancel out. It's referred to as being out of phase. You've experienced this if you've ever kind of played in a pool where you use your hand to kind of splash somebody else, make waves and try to splash them with those waves. Well, if they do the same thing at you, when the waves meet each other, they kind of cancel each other out. They don't make it past one another. The same thing happens here. The waves are out of phase. So the electrons, as long as their wave is in sync with itself, it can exist. If not, then it can't exist. So allowed energy level, not allowed energy level. Or not allowed distance. It wouldn't be referred to as an energy level because the electrons can't exist there. Okay, now we're going to look at the Bohr model in a little bit more detail. I know in the pre-notes I had you copy a bunch of diagrams, so we're going to be filling in those diagrams. Okay, now each one of these energy levels is given a quantum number. Now there's many quantum numbers. You're only responsible for what's called the principal energy level quantum number. N equals 1 would be the first energy level, N equals 2 would be the second, N equals 3, etc., all the way. And theoretically, it goes all the way to infinity. Now notice that as N increases, the energy levels get closer together. This is called convergence. The energy levels get closer and closer and closer and closer together. So now let's look at just one electron. So this electron is in this energy level, moving around. Yes, it's electron waves going around. Well, if we energize that electron, if we pass electricity through it or heat it up, we can cause that electron to go to a higher energy level. Now remember that this electron is there because of the positive charge of the nucleus. If there was no positive charge of the nucleus, that electrostatic force of attraction between the two, the electron would just go along its merry way. But it's attracted to the nucleus. So it remains in orbit. It's kind of like taking a ball on a string and swinging it around your head. As long as that string is there, that attraction between your hand and the ball, which is the string, it'll remain there. And so you have that electrostatic force of attraction between the two. Well, in order for the electron to go to a higher energy level, it would have to gain energy. And so when that occurs, the electron can go to a higher energy level by absorbing energy. So now when this happens, the electron could go to this energy level or this energy level. I'm just using this as an example, this energy level here. So in order for an electron to go from a lower energy level to a higher energy level, it must absorb energy. Okay, now when the electron comes back down, it's going to release energy. But for our purposes here, to understand the emission spectra of the elements, what's going on is that when the electrons come back down, they give off light, and we can see that light. And for this particular transition, going from the 5th energy level back down to the 2nd energy level, it gives off blue light. If the transition is between the 2nd energy level and the 4th and back down, it gives off green light. If it's between the 2nd and 3rd, it gives off red light. Now, I'll be stressing the following in subsequent slides here, but really, really important, this idea that students often get mixed up on. What is happening here is when the electron goes to a higher energy level, this example here goes to a higher energy level, light is not given off. It absorbs energy. It has to be either heated up or electricity passed through it or something, causing the electron to go to a higher energy level. It's only when electrons go back down to a lower energy level do they release energy in the form of electromagnetic radiation. And for these particular transitions, going from a higher to a lower energy level, it's giving off visible light. But we'll talk about other parts of the electromagnetic spectrum in a few minutes. All right, now this is just a linear representation of what we just looked at. It's a little bit easier to talk about and draw. So each one of these are energy levels. This would be the transition between the 5th and the 2nd to give us blue light, the 4th and 2nd to give green, and the 3rd and 2nd to give red. Now, blue light has more energy than red light, so you notice that the wavelengths are relative. Blue light would have a shorter wavelength than green, which would have a shorter wavelength than red. Red is of the three colors, red is less energy. Blue would be the highest. Now, of course, you don't see blue light, green light, red light being given off in different flashes. They're combined together. And you might remember this little animation I showed last time. This is hydrogen gas, electricity being passed through it, and it gives off a lavender color. But if we pass that light through a prism, through a spectroscope, we can break it into its component colors. And so you can see that you have red light, green light, blue light represented here. Now think about what would happen if Bohr was wrong. If the electrons could go any distance and back down again, well then any possible light could be given off, all colors. Every atom of hydrogen would give off all the colors of the rainbow because all transitions would be possible. But that's not what we see. We see this lavender color, and when we break it apart, we see we only have these colors. There's a few others, but these are the only three you're responsible for. We only see those colors. We don't see all the colors. So again, Bohr's model is just kind of an amazing insight that the electrons can't just move around anywhere, or they can only be at certain allowed energy levels. And we know that because we can literally look at the wavelengths of light that are given off as the electrons transition from a higher to a lower energy levels with very specific energies. This is the emission spectrum of the hydrogen atom. So the energy increases, the light, we're talking about energy of the light increases as we go from left to right. As energy increases, the spectral lines converge, get closer together. So if you were asked to identify if you were given the spectrum of hydrogen and you were asked to identify which is the red line, what would be the one that's furthest away from the others? If you were asked to identify the violet line, it would be the one closest to its neighbor. They get closer together. High energy over here, low energy here. Okay, we're going to look at some other transitions. We've only been looking at visible light. Let's look at ultraviolet and infrared. If the transition of the electrons is down to the first energy level, so the electrons, of course, would have to be energized to go to a higher energy level, but when they come back down, if they come back down to the first energy level, ultraviolet light is given off. It's referred to as the Lyman series. If the transition is down to the second energy level, then that is visible light. That's called the Balmer series. Now you're responsible for the three colors, red, green, and blue. What transitions give those specific colors? If the transition is between the third down to the second, that's red light. Fourth down to the second, green. Fifth down to the second, blue. Notice that the second means that it's visible light. All transitions from wherever the electron came from down to the second energy level, that'll be visible light. Down to the first energy level, that'll be ultraviolet. And one more here, down to the third energy level, that is infrared, the Paschen series. Now comparing the three series, ultraviolet light would be the higher energy, and infrared would be lower with visible light in between. Ultraviolet light, we associate that with sunburn, skin cancer, so it's the dangerous portion of the electromagnetic spectrum. Beyond it is X-rays, gamma rays are very dangerous. But beyond infrared is radio waves, not dangerous at all. Okay, let's summarize the Bohr model. Electrons orbit the nucleus only within allowed energy levels. Each energy level is at a specific distance from the nucleus. Within an energy level, electrons do not lose energy. So this problem that we had before Bohr, we no longer have it. The electrons don't travel like that. They travel in allowed energy levels. When electrons are in the lowest energy level available, the atom is in the ground state. So if we think of these two lines here representing two different energy levels, if the electron is at the lowest one possible, we would say the atom is in the ground state. Now, we don't say the electron is in the ground state. We would be referring to the atom itself. Now, remember, we're only talking about hydrogen, so hydrogen just has one electron. When electrons absorb energy and move to higher energy levels, the atom is in the excited state. So if the electron were at a higher energy level than normal. Now, a good analogy for this would be throwing a tennis ball up in the air. If we throw the tennis ball up in the air, we could think of the tennis ball being in the excited state. But when it comes back down to the lowest point possible, then it's going to be in the ground state. When an electron returns to a lower energy level, it will give off electromagnetic radiation with energy exactly equal to the difference found between those energy levels. So the light that's given off, we can measure that with a spectroscope, know exactly what its energy is, and know exactly what energy level transitions occurred to give off that specific type of electromagnetic radiation. What did the Bohr model explain? It explained how electrons could orbit the nucleus without losing energy, and it explained the emission spectrum of hydrogen. What were the shortcomings of Bohr's model? Shortcomings meaning problems. It could not explain the emission spectra of elements other than hydrogen. Hydrogen, remember, only has one electron. So, no small feat by any means, but relatively easy to do because the other elements have more than one electron, and it becomes exponentially more difficult to describe the emission spectra of those elements using Bohr's model. And also, Bohr's model could not explain the chemical properties of the element. And of course, that's what we're after. We're trying to understand why the elements behave the way they do. Bohr's model offered no explanation for the chemical properties of the elements. But Niels Bohr did not develop his model and walk away. He, without missing a beat, marched right into the final chapter of atomic theory, and that's quantum mechanics, which will be our topic for our next set of notes. End of notes.